Hi, and welcome to Optimizing Game Performance with the Radeon Developer Tools Suite. I am Chris Hessick, and together with John Alper, we will introduce you to the different tools in the suite and show some of the new features that we have added in the last year. And in part 2, we will show you some of the collaborative work we are doing to support external tools development. So let's get started by reviewing the Radeon Developer Tools Suite and see what's changed since last year's GDC. The Radeon Developer Tools Suite currently consists of 5 main tools, each specializing in one area of GPU optimization. The Radeon GPU Profiler, or RGP for short, is the original member of the suite and allows the developer to get a low-level view of how work is executed on the GPU. It gives a view of activity on all the GPU queues, command buffer submission timings, synchronization, and barriers. Coupled with instruction-level data and hardware counter information, the Radeon GPU Profiler is the go-to tool when optimizing for AMD GPU hardware. The Radeon Memory Visualizer, or RMV for short, tracks the usage of GPU memory over time and allows you to create snapshots of how the memory is being used at a specific time. You can see which resources require the most memory, the heaps they are in, and how the heaps are sub-allocated. It is also useful for detecting memory oversubscription, fragmentation, and locating memory leaks. The newest member of the suite, released in July 2022, is the Radeon Ray Tracing Analyzer, or RRA for short, which gives you a high-level view of the acceleration structures used in your application. It makes use of traversal counter heat maps that display how arrays interact with your scene, revealing hotspots for loop count, instance hit, box volume hits and misses, and triangle hits and misses. Radeon GPU Analyzer, also known as RGA, is an offline compiler and code analysis tool. Using RGA, you can compile shaders and kernels for a variety of AMD GPU architectures to generate RDNA disassembly, hardware usage statistics, and static analysis reports, such as VGPR pressure analysis. All of this can be done independently of the installed GPU, meaning that, for example, you don't have to have the latest RX 7000 series GPU physically installed in your machine in order to analyze shaders and kernels for that architecture. RGA is available as a command line tool which supports several APIs, such as DX12, DXR, Vulkan, and OpenCL. It also has a graphical user interface that supports Vulkan and OpenCL. The fifth, and perhaps the most important component of the suite, is the Radeon Developer Panel, or RDP for short. The panel provides the communication channel that delivers requests to and receives data from the AMD Radeon Adrenalin driver. RDP provides the data used by RGP, RMV, and RRA, and can be used locally or remotely over the network to connect to other systems running the Adrenalin driver. The Radeon Developer Tools Suite can be downloaded from gpuopen.com, and you can also find introductory videos for all of our tools on the videos page. Since last year's GDC, the tools team has been busy adding smart access memory support to RMV 1.4, ray tracing perf counters, and DXR 1.1 style inline ray tracing support to RGP 1.13. In May, RGA 2.6.1 added support for the mobile 680 GPU. RMV 1.4.1 for Linux was released in June, and in July, RGP and RGA had minor updates. But the big news was that we also released the first version of the Radeon Ray Tracing Analyzer. For the rest of the year, the team focused on support for RDNA 3, adding ray tracing support to RMV, adding new features to RRA and RGA, and support for the HIP API, as well as HIP and OpenCL instruction timing, and additional ray tracing support to RGP. Let's take a look in detail at some of these changes. Starting with the Radeon Developer Panel, we have improved the usability of the UI for customizable workflows. And we have added a new system information pane with the ability to export the information in JSON format. Other than these small changes, work on the panel has focused on support for RDNA 3 and on stability and bug fixes. Now, let's talk about the Radeon GPU Profiler. As mentioned, we had 2 major releases, versions 1.13 and 1.14 in the past year. We also had two smaller point releases, 1.13.1 and 1.14.1, to pick up some key bug fixes. When planning both major and patch releases, we consider any issues reported on our GitHub issues list. So if there are things that don't work right for you, or if you have suggestions for improvement, please let us know. As mentioned earlier, one of the largest things we did over the past year was add support for our latest GPUs, the RDNA 3-based RX 7000 series. While most of the work was done under the hood to support all of the existing RGP features on the new architecture, there are a few places where new hardware features have been surfaced in the RGP user interface. First, the device configuration page has been updated to display the size of some additional caches. Here we can see that the size of the Infinity cache, the instruction cache, and the scalar cache have been added. While this support was added for RDNA 3, it will also be shown when viewing a profile captured on older RDNA 2-based RX 6000 series GPUs. One other thing to notice here is the increased number of vector registers per SIMD. Here, on a 7900 GPU, we see 1,536 vector registers per SIMD, while on older RDNA 1 and 2 based hardware, there were 1,024 vector registers per SIMD. One reason for this increase was to better support ray tracing workloads. Here we can see the same ray tracing workload visualized in RGP on both an RX 6000 series card and an RX 7000 series card. On the 6000 series card, this workload only achieves about 50% wavefront occupancy and takes about 2.25 milliseconds to execute. Due to the higher number of available vector registers on the 7000 series card, the same workload can achieve 75% wavefront occupancy, which in part helps to reduce the duration of the event to less than a millisecond. This specific benefit of the newer GPUs can easily be seen in RGP. We can also see higher occupancy achieved for some non-ray tracing workloads, which also appear to have benefited from the increased number of registers. One of the new hardware features in RDNA 3 was the addition of new Wave Matrix Multiply Accumulate, or WMMA instructions, which can accelerate certain matrix math operations used in AI or deep learning applications. These new instructions are fully supported by RGP's instruction timing feature set. In addition to providing instruction issue latency information for these instructions, the instruction timing side panel also shows the number of WMMA instructions executed by a shader. In addition to supporting the latest GPUs, the RGP team also added some new ray tracing features this year. More and more games are using DXR 1.1 style inline ray tracing instead of traditional ray tracing pipelines. Several parts of RGP have been enhanced to make it easier to identify workloads which are performing inline ray tracing. First of all, the API Shader Stage UI element that appears in several of the RGP views has been updated to paint shader stages that use inline ray tracing a bit differently. Here, the top three examples show the traditional look of the shader stage UI. The bottom two examples show how the UI looks when a stage is using inline ray tracing. As you can see here, a shader stage box is colored using a gradient red color when it uses inline ray tracing. One example where this is done is in the Pipelines Overview pane. Here we can see a few yellow compute pipelines that are colored with the red gradient, indicating that those compute shaders are performing inline ray tracing. Similarly, here in RGP's most expensive events pane, we can see individual compute events that are performing ray tracing. And here in the instruction timing pane, we can see the same UI control, indicating that the shader performs inline ray tracing. In this pane, we can take it a step further to see the hit count and latency of the individual ray tracing instructions. We can also see the total number of ray tracing instructions executed by this shader. In addition to letting you know which pipelines and which events perform inline ray tracing, recently added coloring modes in the wavefront occupancy view can let you see which regions of GPU activity were executing shaders that perform ray tracing. Here we can see the default coloring mode for a frame that performs inline ray tracing. Other than the beginning of the frame where the acceleration structures were built, we don't have a clear idea of where within the frame the ray tracing is performed. By selecting the Color by Ray Tracing mode in both the upper wavefront timeline and in the lower event timeline, we can easily see which parts of the frame are doing the ray tracing work. Wavefronts from events that perform ray tracing are now painted as red, while all other waves are painted as gray. Similarly, in the lower event timeline, events that perform ray tracing are painted in red. Now, in addition to seeing the red section which builds the acceleration structures, we can also see the second red section where the frame is actually tracing the rays through the scene. Another recent enhancement to the ray tracing feature set in RGP is support for ray tracing events initiated by an execute indirect call. In earlier versions of RGP, while these events were identified as ray tracing events, the pipeline state pane did not show the ray tracing flowchart or shader table like it did for dispatch rays calls. Now, RGP treats execute indirect events and dispatch rays events the same. In both cases, when the indirect compilation method is used, you can see the ray tracing pipeline flowchart, which lets you know which stages of the pipeline are the most expensive. You can also see the shader table, which helps you understand which individual shaders within the ray tracing pipeline are the most expensive. Another new feature added to RGP this year was support for the HIP API. HIP, or the Heterogeneous Interface for Portability, is AMD's dedicated GPU programming environment for designing high-performance kernels on GPU hardware. HIP is a C++ runtime API and programming language that helps developers to create portable applications on different platforms. I'm not going into too much detail here, but if you have a compute application built using the HIP API, that application can now be profiled with RDP and RGP. On the left side here, we can see a HIP profile where several HIP APIs and kernels appear in RGP's event list. As part of the work to support HIP, we have now enabled support for the instruction timing features for both OpenCL and HIP. As we see on the right here, we can now show low-level performance data for compute kernels the same way we've been able to for DX12 and Vulkan shaders. The last thing in RGP I want to talk about is an upcoming overhaul of the UIs that show disassembled ISA instructions. As you may be aware, there are two places in RGP where we show shader ISA disassembly, the pipeline state pane and the instruction timing pane. And while the two views are similar, there are some subtle differences in the way ISA is presented to the user. Syntax highlighting is slightly different, and some information, like line numbering, opcodes, and addresses, is shown in one view but not the other. To resolve some of these differences, and to make sure that both panes can take advantage of new features when they are added, we are taking the time to refactor and reduce some technical debt in these views. As part of this work, we are also adding some frequently requested new features. First, we are making it possible to collapse and expand blocks within the ISA, so that you can quickly and easily hide an entire block when it is not of interest. For example, in the instruction timing pane, due to branching and control flow, some entire blocks may have a 0 hit count. In this case, we may choose to collapse these blocks since they may not be of interest to the developer. Another frequently requested feature is the ability to select some text in the disassembly and have the view automatically highlight other instances of the selected item. With the new ISA view, by simply clicking a specific item in the ISA, you'll be able to see all occurrences. This works for instruction opcodes, registers, and constants. We are also making it easier to follow the control flow through a shader. When you select a branch instruction, you'll be able to quickly jump to the target of that branch. When selecting a label, you can quickly jump to any branch instruction whose target is the selected label. In cases where multiple branch instructions reference the same label, you'll be able to choose which one to jump to. As part of this feature, the ISA views will also maintain a history of navigation followed by the user. After following a few branch targets through the shader, you can use these navigation controls to quickly go back and forth between branches and targets. We are also giving the user more control over which columns are shown. So if you decide you only want to see the instruction opcodes, but not the arguments, or the offsets, you can customize the view to your liking. One other subtle change that will make it easier to know where you are within a shader is that the label associated with the current code block will always be visible, pinned to the top of the view. So if you're scrolling through a shader's disassembly, you can quickly see exactly which part of the shader you are looking at. The plan is for this new ISA view to be included in the next major RGP release. As part of this work, we have written the new ISA view code such that it can eventually be used in other tools, like the Radeon GPU Analyzer, which also displays shader ISA. Our longer-term goal is that any AMD tool that shows ISA code will do so in a consistent manner using this new view. All right, that wraps up my portion of the presentation. I will now hand things over to John to talk about some of our other tools.
Thanks, Chris. And hi, I'm John Alper, and as we mentioned earlier, we released the Radeon Ray Tracing Analyzer version 1.0 in July 2022, and updated it with RDNA 3 support in version 1.1 in December. Today, I'm only going to be talking about the recent updates to RRA, but if you want a full and more extensive introduction to the tool, there is a video available on GEP Open at the address shown on screen. With the new RDNA 3 architecture, the AMD Adrenalin driver has been upgraded to include new acceleration structure features, such as instance re-rating and triangle splitting. These features improve the spatial coherence, meaning that the new arrangements of the acceleration structures reduce the traversal operations, resulting in fewer cache misses and so on. In some cases, these features may include acceleration structure to occupy larger memory or may take slightly longer time to build. But overall, these features are automatically activated by the driver, so no user input is required. The Radeon Ray Tracing Analyzer UI has also been updated to visualize these new features. The first feature I would like to cover is the instance re-rating. Based on the instance transform and BLAS complexity, the driver may decide to re-rate an instance. Re-rating in this context means the act of embedding the immediate child nodes of a root node from a bottom-level acceleration structure directly into the top-level acceleration structure. To the ray tracing application, the re-rating is fully hidden, again, which means that there are no changes required from the user. As you can see with the new example on the right, the instance bounds are filling the entire space, which may be expensive to traverse. As opposed to re-rating, which can improve the layout of the structure to save upon traversal costs. As part of the 1.1 update to RRA, we have provided some features to discover and understand how re-rating was used in your acceleration structures. To start with, using the geometry coloring modes, you can switch to color geometry by re-rating. This will highlight the re-rated instances in the TLAS viewer. You can then select the re-rated instances. When you select the re-rated instances, the node information panel on the left will show the re-rate siblings. You can select each sibling from here to navigate around instead of selecting them through the 3D viewer. The next driver feature is the triangle splitting. This feature is like re-rating, but it is done on the bottom level acceleration structure. The driver will automatically split the bounding boxes that point to the same triangle based on size and orientation. These split bounding boxes point to the same geometry and primitive index. In the image on the left, you can see an example of long triangles that are diagonal. Here, yellow means more expensive traversal. The image on the right has a similar structure, but the cost of traversal is more localized thanks to triangle splitting. Just like re-rating, no user input is required. We also have similar UI features for triangle splitting. You can choose the triangle splitting coloring mode on both TLAS and BLAS viewers. Once you select the split triangle, you can see all the split triangle siblings and quickly switch between them using the node information panel on the left. These are the new acceleration structure features that we have released with RRA 1.1, but we also have two new upcoming features on our 1.2 release. Our first upcoming feature is the Instance Mask Filter. With this feature, you can now mask or filter out the instances on a TLAS, just above the 3D viewer. You can click on each bit to enable or disable it. You can also copy and paste the mask as hex into RRA, into the right side of the Instance Mask Filter widget. With each change to the mask, RA will update the viewer on geometry coloring and traversal counters appropriately. Our next upcoming feature is a histogram for the real-time traversal counter rendering mode. This histogram will display the distribution of the counter values across the traversal counter spectrum. It will now also display the average counter number across the traversal counter rendering. In this example shown here, we can see that the peak of the histogram is in blue-green range, indicating that the average traversal count is on the lower side. If the peak was in the orange-red end of the histogram, it could indicate that the average traversal count is high and optimization could be required. Before moving on to Radeon Memory Visualizer updates, I want to point out that we have more detailed overview and introduction to RMV on GPOpen at the address shown on screen. RMV Update 1.4.1 added full capture and visualization of results on Linux for Vulkan applications. And full ray tracing support came online with an AMD driver update for the RMV 1.5 release. This screenshot shows the RMV timeline view where the GPU memory usage is recorded for a sequence of gameplay. The RMV trace files are relatively small and contain the lifecycle and type information associated with each allocation. As you can see in the color key, the ray tracing resource type is represented in colored turquoise. RMV allows you to create snapshots within a memory trace. These are deep dives into the usage state of GPU memory at specific moments in time. Here's an example of the heap overview pane of one of the snapshots, displaying that smart access memory is disabled, and that local memory is oversubscribed. On the right-hand side, circle charts provide usage summaries of local, invisible, and host memory heaps. Ray tracing related memory allocations are clearly visible. The resource overview pane displays the resources as a block chart with the largest allocations in the top left. Useful summaries of the total amount of memory available and the memory used by your application. In this example, a ray tracing resource has been selected and its details are visible at the bottom. The allocation overview pane lists the allocations by size and supports numerous sorting methods to visualize them. One of its most useful features is the display of memory fragmentation. As shown here, colored by type, the sub-allocations for placed resources can be seen, each separated by unbound memory in gray. This view allows us to visualize the efficiency of our sub-allocation. Double-clicking on an allocation will open it in the Allocation Explorer. In this view, the allocations are listed in a table at the top. And when one is selected, the placed resources or sub-allocations are listed in the table below. The Resource List pane displays a list of all the resources present in the snapshot with some useful summaries in the charts at the top. Double-clicking on a resource opens it in the Resource Details pane, showing the detailed resource information in the top half and a timeline of lifecycle events in the bottom half. The Radeon GPU Analyzer had several incremental releases in the last year, but we are going to focus on the new support in the latest update 2.7. RGA 2.7 added a support for RDNA 3 hardware in DirectX 12, DXR, Vulkan, OpenGL, and OpenCL modes. We also introduced a new VGPR pressure visualization feature in the GUI application's disassembly view. Let's have a quick look at this powerful new feature. After successfully building your code with the RGA GUI app, you will notice a new column in the disassembly view named VGPR pressure. The column header text format is VGPR pressure used X allocated Y over 256, which provides a summary for the entire shader, where X gives the total VGPRs used by the current shader and Y gives the total number of VGPRs allocated. Hovering over any of the column cells will show a tooltip that is designed to provide a summary of the live VGPR at the specific instruction and hint about how many VGPRs needed to be reduced to save a VGPR block at that instruction. Note that VGPRs are allocated blocks, which vary in size. The VGPR block size is determined by the target GPU and in certain cases by specific characteristics of the shader, such as the wave size it was compiled for. The hint indicates how many VGPRs need to be freed to free up an entire block of VGPRs at that point of the shader. When examining the VGPR pressure column cells, in addition to the numerical value, which gives the number of live VGPRs at that instruction, you will also notice a utilization bar that visualizes the VGPR usage and the VGPR block utilization. The emptier the utilization bar is, the less of the allocated VGPR block is being utilized, which means that the fewer VGPRs would need to be reduced to free up that block. When dealing with shaders that have thousands of instructions, it can be hard to identify what matters, the hottest points in the shaders in terms of VGPR pressure. With RGA 2.7, you can jump to the hottest areas in the shader with one click. Since it can happen that multiple areas in the shader will have identical maximum pressure, the tool also allows you to iterate forward and backward through the disassembly lines with most pressure. One final thing we want to mention before switching gears is that there is support for several of our tools built into the open source RADV driver that is included by default in Linux distributions, such as in Ubuntu 22.04. RADV, which is part of the Mesa project, is a community-supported Vulkan driver for AMD Radeon GPUs, and it is the driver stack that supports Valve's Steam Deck handheld gaming device. One of our goals has been to open source our tools code, a goal we have been achieving gradually. The Radeon Memory Visualizer was open sourced in 2020, and the Radeon Ray Tracing Analyzer was open sourced in December last year. As part of our commitment with GPOpen, we have been contributing directly to other open source initiatives, notably GFX Reconstruct and RenderDoc, to support ray tracing. While providing our own AMD hardware-specific tools, the tools team support external tools such as Pix on Windows and RenderDoc with plugins and libraries to support hardware counter gathering on AMD GPUs. Let's take a look at these tools in a little more detail. Pix on Windows allow you to debug and analyze the performance of your D3D12 PC game title. AMD contributes to Microsoft Pix on Windows by supplying a plugin to help you analyze the performance of your game titles on AMD Radeon hardware. The AMD Radeon plugin is included automatically as part of the Pix on Windows installation. The AMD Radeon plugin supports collecting per draw call event list counters and high-frequency counters that appear as graphs on the timeline. It supports the measuring of the wave occupancy along with the wave occupancy limiters, and coming soon will display the same cache utilization and ray tracing graphs that you have seen in our Radeon GPU profiler. RenderDoc is a free MIT-licensed standalone graphics debugger that allows quick and easy single-frame capture and detailed introspection of graphics state and resources. It supports applications using Vulkan, D3D11, OpenGL, OpenGL ES, or D3D12 across Windows, Linux, Android. RenderDoc was created by Balder Carlson. The tools team have been working on bringing ray tracing support to RenderDoc, starting with DXR and closely followed by Vulkan ray tracing. DXR support is a work in progress and not yet fully upstreamed. We have been working on adding the capture and replay of DXR workloads and enabling developers to visualize and inspect DXR events. We plan to continue contributing additional features, including Vulkan ray tracing. The team has also added RDNA 3 hardware support to the hardware counter library used by RenderDoc. RGP interop is an interesting feature in RenderDoc that you may not be aware of. RGP interop is the ability to generate a Radeon GPU profiler trace directly from inside a RenderDoc playback. RenderDoc is not intended to be a profiler, as its playback performance is limited by its needs to be an effective debugger. Therefore, RGP profiles produced by interop are not representative of the performance of the original running application. However, interop does have a very useful feature. It allows you to select a draw call in RenderDoc and open the corresponding event in RGP to view the related GPU activity. This link between corresponding events also works going on the other way from RGP to rendered dock, allowing you to investigate the GPU resources and state related to low-level activity on your GPU. We now move to GFX Reconstruct, also known as GFXR. For those unfamiliar, this is a software suite developed by LunarG, which captures and replays graphics workloads. Its central purpose is to record graphics API calls to disk and replay them back. GFXR is a free-to-use and open source. It started as a replacement for VK-Trace and has seen wide adoption by Vulkan developers. We are happy to say that earlier this year, through a joint venture between AMD and LunarG, support for D312 and DXR has been added to GFXR. This means that D3D12 developers have yet another valuable means to repeatedly analyze their latest ray-traced workloads. The software architecture of GFXR is also extensible, meaning that users could extend it to record other APIs and or replay the workload in a manner that suits them. You also get to decide how many frames to capture and replay. GFXR allows for recording of the process lifetime or of smaller segment within it. During GFXR's development, we have also kept a close eye on performance to ensure that the tools remain lightweight. We like to think of GFXR as a huge toolkit, which can be used as a platform for experimentation. Inside the box, we find components for capturing and processing the GPU workload. Capture-side components come in form of DLLs. For Vulkan, capture is implemented as a layer. For D3D12, capture is implemented in proxy DLLs that replace and call into the runtime. In the end, you end up with a single GFXR file that contains everything you need to replay. Processing these .gfxr files is done by executables. The most frequently used capture file processing tools are gfxrecon-replay.exe and gfxrecon-optimize.exe. The gfxrecon replay tool replays capture files, and the gfxrecon-optimize tool produces new capture files with improved replay performance. There are also other tools that can display the capture file metadata, change the compression algorithm, generate a human legible API dump, and more. Remember that since GFXR is open source, there's really no limits to its use cases. Users can write their own tools to interpret the recorded file to suit their own purposes. Some sample use cases are debugging visual artifacts, repeatedly profiling the same workload, and running GPU stress tests. It's up to the user to decide what they want to do with GFXR. You could grab a binary, or just build it yourself. It's easy to build, it only takes about a minute. And if you want to participate in its development, you can do that too by issuing a pull request. Please visit the websites linked here. That brings us to the end of this presentation. To download Radeon Developer Tool Suite and watch more videos from the team, please visit gpopen.com. Thanks for watching until the end, and goodbye from Chris and myself, Can Alper.